So let's start with the first case. The first case is about forestry. We made a survey with our SLAM scanner X120 Go and our UAV LiDAR solution XFLY together. It was a combined survey in the northern part of Italy, and specifically in the Dolomites, which is a very nice place. The goal of this survey was to map and to understand the forestry asset of this area and to perform some terrain analysis, in particular for the estimation of the biomass that can be extracted from these resources. So we combined together two scans. The dimension of the survey was approximately 6 hectares, and we obtained a precision around 3 centimeters, combining the two data sets. So with the XFLY, we made a very short fly, about 8 minutes of flight, collecting this data at a height of about 80 meters. And with the X120 Go, we performed the survey around the trees of this area in about 10 minutes. So I leave the word to the more expert speakers that will explain to you how to use this data in Aplitop software.
Hey, thank you, Chiara. Hello, everyone. I'm Francisco Vázquez, software engineer here at Aplitop. And yeah, let's begin with the use case and let's see the basics and how to do some ground extraction and terrain modeling. So, first of all, we have to create a new project. So we call it something like Forestry. And here we have our empty project. So we're going to go to point clouds and just import our dataset. So here we can see we go to our folder here and we have the two last files, the one from the XFLY and the one for X120 Go. And we add them and we can see here all the available formats that we support in the application. So you can work with last file, 57, PLY files, Recap file, LGSX, and you can even import ASCII files and set up the column configuration, the limiters, and so on to use a custom format. And we add those files and import them. Okay, so now we can see here we have our points in the application. We are watching in the viewer. Our next step will be to analyze and check the information we're given. So we select both of the point clouds and check their properties. And here we can see that we are talking around 135 million points. And we can see the bounds of the coordinates here from the point clouds. And most importantly, here at the bottom, we have all the attributes that were detected during the import process. So in this case, we have everything except categories, except classification. We have color, we have intensity, the timestamp values, and from the LiDAR, we got the return information from the LiDAR. So if we want, we can go into the details of any of these fields, and it can show us for continuous values like intensity. It will show us an histogram and show the distribution of the values of that attribute. So we can see here how the intensity is in this case. And if we go to a discrete value like the return info, we can see the classes of returns like unique versus many and less of many, and how are distributed along the point clouds in this pie chart. With the classification, which is also a discrete, will be very similar. Okay, so now we know what we have available. So our next step will be to uh, do a quick visual analysis with the different symbologies to check for issues or how to clean the point cloud to get the ground. So let's start with the cloud representation. And as you notice, we have the both of the point clouds, and they have those colored rectangle, which is the color that represents that point cloud in the project. So when I go to cloud, you can see the yellow point cloud and the red point cloud, which represent the XFLY, the yellow one, and the red one is the SLAM one. So we're going to enable the EDL to not see everything flat. And we can focus here to see in more detail the SLAM overlap in the LiDAR dataset. We can even hide the XFLY, for example, to better see the SLAM one. And we're going to use them as a single point cloud in this case, just to use the reinforcement given by the SLAM dataset to get more ground information in that area. And here we can also see the return data. This is with the class of return. So the blue ones are the unique return, as you can see here in the legend. And the yellow ones are free of many, and the red one are less of many. As we have two returns, there won't be intermediate in this case. And we can also analyze the intensity. For example, we can go here and set the representation, and we can configure all the colors and the distribution as we want. We're going to tell it to use 100 ranges and distribute it with quantiles, which is more accurate for the intensity values. And here we can see the values of the intensities. This can be useful to detect when you have a very reflective area and you have like a hole in the point cloud. This is very useful because you will see a very bright ring around the hole, so it's very easy to spot this kind of things. And now we are going to go to the elevation map. And here, this is going to help us to detect high and low noise. We're going to see now, we are going to configure at 20 ranges with this color palette. Of course, we could change with any of these pre-configured color palettes or change here any color we want. We can set up this as we wanted. And now we're going to see that we can see the 20 colors well because we have a noise at the top. Likely, this confirms that at the bottom we can see the magenta color. That means that there are no low noise. That's very good because low noise makes harder to extract the ground, and we have to clean that very well. So now we are going to handle the cleaning to get the ground. First thing we're going to do is get rid of all the points that we know for sure that we don't need. So these top points here of noise, we can just simply zoom a little bit and make a broad selection, taking care of not selecting any of the actual point cloud for not losing any detail. And all of that noise directly remove those points. So that's the way the application works. You make a selection either manually or with any of the filters or any tool. And once you have the selection, you decide what to do with that. You set a category, you delete, make a filter, hide the points, whatever you want. So now we're going to use the return information because as we are looking for the crown, we know for sure that intermediate and first of many can be ground points. So we are going to directly select them and we're going to get rid of them. And also with this, we're going to reduce the number of points and make the rest of the process a little easier for the computer. So now to get rid of the rest of the noise points that we see here, we could do it manually, but it will take a lot of time and we have to be very careful. So instead, we're going to use the isolation filter. What we're going to do is find points which at the radius of zero point 0.2 meters don't have at least two neighbor points. If that criteria is not match, we're going to consider that an isolated point, and we're going to select every one of them. And we're going to see here all the noise points are selected, and also at the borders, because we don't have as much density, are going to select a lot of points also, and some between the trees, which is to be expected with the vegetation, but it should be okay also because we are looking for the ground. It won't affect for further calculation, so we're going to just remove them. As you can see, the vegetation looks almost the same, but we got rid of all the noise. And now we go to the ground extraction. So for that, we have a special filter, which is called a CSF or closed simulation filter. This is this one over here. And this filter will uh, find the ground by making a grid with a point cloud inverter on the set. So it's very weak against low noise points, and also at the borders you're going to see, because we don't have so much density and we miss the ground points. There is where we can have more issues, but we'll fix it later. So we run the filter at the resolution of zero point 0.2 meters and let it work to find the ground. And now we can see selected all the points that it considered that are not ground points. Let enable ideal again. As you can see, all the vegetation is selected, also some of the low vegetation. This filter let's invert the selection to select the ground. And also this filter can have issues when the slope is very strong, very steep. Like in here, for example. So let's very quick fix this with a manual selection and add these points back to the selection. Okay, so now we have the ground selected, so we move all those points to the ground class. And now that we have a classification, the category representation is enabled. So we can switch and we can see of the white points, which are the ones non-ground, and the orange ones, which represent the ground. And we can go here to the property of the classes, and we can enable or disable points of any of the classes, so we don't see them. And also with this column here, we can tell it if we want to triangulate those points. What that does is it doesn't matter if they are visible or not, they won't be considered either for modeling or for a profile computation. In the profiles will be ignored also. So we hit OK, and now let's check the result from the raw filtering. And we can see that we still have some points of vegetation here. So we're going to fix some of them by manually selecting and removing the points. And also remove all this over here. And also another way of cleaning the point cloud could be like this. We can go here and we can see here it seems to be like car parts from cars that were in that road. So we can do a profile here from the top view, and with the dynamic assignment, I'm going to select the bandwidth by selecting points graphically. And let's make sure that in our profile, we take those points. And here we see the points profile. And directly in the profile, I can make a selection, take all of those points. And I can see also here that there's some vegetation. I can select it also. And you can see that in the 3D view, the points are also selected. So the profile and the 3D view are linked, and I can make even decisions with the selection in the profile itself. In this case, we're going to switch this to the never classified class, which is the non-ground class for this case, and move those points there. And because earlier I disabled that class, the points disappear, and we fix those areas. So with a combination of keep applying the CSF filtering in localized regions, manual filtering, and using the profile as a reinforcement, we can clean the ground and get something like this. We can now even show the rest of the point cloud to see everything, as the non-ground points are not triangulable. No issues with that. You can see here the full result. And finally, we can go to modeling and create our digital model. So we have two ways of creating models. We have the elevation map, which creates a grid of heights with squares, or a triangulation. In this case, we're going to use a triangulation because, as you saw earlier, by the cleaning process, we get holes because the low vegetation and so on. There are places where we have no ground information. So the grid can fill those holes by interpolating the vertices, but it's most costly and it tends to be less precise that let the triangulation works. Triangulation is better for this kind of data. So we're going to use a resolution of 0.25 and a maximum edge of 25 meters around the contour. Here we can also have the option to include a contour for the triangulation with a 3D polyline if we want. And even we can have in the project, in our drawing, break lines, 3D polylines of break lines, and introduce them into the triangulation to supply missing information and things like that. If, for example, when we are modeling something that has like a road and we want to have very clear definition of the road lines, that a way to do a polyline and insert it. So here we have our triangulation. As you see here, we can change its representation similar to point clouds. It's exactly the same. We have the model, which is a flat color, the elevation map, and a slope map, a slope direction map, and even we can import an orthophoto and texturize the model with the orthophoto if we want. Okay, so that's our model in completely solid. And now we can compute the contour lines. So we're going to use an interval of 1 meter for minor contour lines. And for the major ones, we're going to use 5 meters. And let's compute the lines. And here you can see the contour lines. And if we zoom in, you can see, and this will happen always, there will be like little spikes in the contour lines, which is inherent to the way that point clouds work, because we always have some kind of margin of error in the point cloud, and the surface captures everything as it is. So a quick way to get a better looking contour lines is we take the surface and we convert it to a data elevation map with the same cell size as our minimum edge length. Okay, so here we have our grid. The grid works exactly the same as the surface, and we can smooth the grid. So we give it for the smoothing a radius of a little more than the cell size and 2 iteration, just a touch. And here we have our smooth model. You can already see that a lot of the bumps are smooth out. And if we compute the same contour lines from this model, you can see that we have a much better looking result. So, of course, this can be a destructive process and you could be afraid of losing the real information from doing that. How can we check that we have not given too much smoothing with making a profile? So we enable everything and we're going to set up a quick profile in the top view with a resolution of 5 centimeters. And we're going to follow this row over here. And as you can see, now we are seeing the section all of the elements. We have the point cloud, the smooth terrain, and the original terrain. The yellow one is the original, the red one is the smooth. And we see the points at the background. And we can check here how the surfaces adapt to the original ground. And we can even make just here and take measurements. We can see there's a diff of 1 centimeter. And if we measure here, we can see that there's a difference of 7 millimeters. So like that, we can check all the elements we want in with any section, and we can see the result. And here is the final product with the only the ground and the final contour lines.